Imagine locking the deadbolt on your front door, right? You set a state-of-the-art security alarm, you go to sleep, completely unaware that the architect who built the house.
Left a massive invisible window wide open on the second floor.
Exactly. Like that, wide open, and before you've even had a chance to realize the blueprint was flawed, someone is already climbing through it.
Yeah, not a great feeling to wake up to.
Not at all. So welcome back to Cyber Mornings Daily here on our deep dive. Whether you're a security professional pulling up your terminal for a morning stand-up or just an insanely curious tech enthusiast trying to avoid, total information overload.
Which is hard to do these days.
Oh, impossible. But our mission today is to cut through all that noise. We are delivering a concise, high-signal cybersecurity briefing, and we're focusing entirely on defender actions.
Right, because we are looking at a fundamental shift in the continuum of defender control today. We're exploring 3 really distinct vulnerabilities, and they all highlight this rapidly shrinking exploitation timeline. I mean, attackers are compressing the window between disclosure and weaponization down to, minutes.
Minutes. It's wild.
It is, and it's fundamentally altering how we have to approach incident response, across self-hosted environments, cloud infrastructure, and the open source supply chain.
Right, because in cybersecurity, time is essentially the ultimate currency. And right now, attackers are using AI to basically bankrupt defenders of their time. So let's start on a self-hosted end of that spectrum where you own the infrastructure and, you bear the entire burden of speed.
Yeah, the hot seat.
Exactly.
Okay.
Okay, let's unpack this. We're looking at GitLab CVE 2026-19478.
Right.
This is a CVSS 9.4 code injection vulnerability, and it impacts both community and enterprise editions. It basically allows an unauthenticated attacker to manipulate or delete publicly accessible projects.
And rewrite data without credentials.
Yeah, no user interaction required at all. And what makes this really critical is the vector, right?
Yeah.
It's exploited via GraphQL directive.
Yes.
So to put this in perspective for anyone who's, used to standard REST APIs, think of a REST endpoint like ordering from a really rigid set menu at a restaurant. You ask for a specific item, the kitchen prepares it exactly as defined, hands it back.
Right, very controlled.
But GraphQL, by contrast, is like handing the customer the entire pantry inventory and just letting them write their own complex recipe for the chef to execute.
Which is incredibly efficient for the client.
Super efficient. But it requires the server to rigorously validate every single nested request. Because otherwise, the customer might be secretly asking the chef to, burn the kitchen down.
Exactly. And that flexibility of GraphQL is exactly where the risk lies. I mean, threat actors, they hunt for edge cases in how those really complex nested queries are parsed by the server.
Right.
So in this specific GitLab flaw, the vulnerability centers around a directive called @grul introduce.
@grul introduce. Okay.
Yeah. And directives in GraphQL are basically instructions that alter how the query behaves. So if the backend parser fails to properly sanitize the input routed through that specific directive,
The attacker just escapes the logic flow.
precisely, they escape the flow and achieve arbitrary code injection. The server just executes the malicious payload because it assumes, hey, this is part of a legitimate database operation.
Wow. Okay, so the mechanics are definitely concerning. But the timeline here is what really shifts the paradigm.
Oh, absolutely. What's fascinating here is the speed.
Because watch how the exposure management firm, they took the initial disclosure and reproduced the exploit internally in, a matter of minutes.
Literally minutes, yeah. And shortly after that, they started seeing active, in-the-wild exploitation attempts hitting their honeypot networks.
That's just nuts. Like, if threat actors are moving from a vulnerability announcement to active exploitation in under an hour, does this mean the traditional patch cycle is officially dead?
I mean, honestly, yes. The traditional patch cycle, where you schedule a maintenance window for next weekend, that relies on the assumption that attackers need time to manually reverse engineer a vulnerability.
Right. Human time.
Exactly. But AI has entirely broken that assumption. Attackers are deploying large language models to automate patch diffing.
Oh, wow.
Yeah, so when a vendor like GitLab releases a fix, they push a binary change, right? AI tools can instantly compare the pre-patch and post-patch binaries.
So they see exactly what changed.
Exactly what sanitization logic was added, and they use that delta as a highly detailed map to understand the underlying flaw.
And then just dynamically generate a working exploit for the unpatched versions.
Yep. The time advantage we used to rely on is just gone.
So the immediate action item here for anyone listening who manages an internet-facing GitLab instance.
You need to bypass the standard testing queue entirely.
Right. Upgrade to patched releases immediately. That's 19.2.4, 19.1.6, 19.0.8, or 18.101 But given that AI speed, just applying the patch isn't really enough to guarantee security, is it?
No, not at all. Patching only stops future attacks. Because that exploitation window is so impossibly tight, you basically have to operate under the assumption of a breach.
So shift into threat hunting.
Immediately. You need to query your web application firewalls, check your load balancer logs, specifically look for requests containing that string @GL introduced.
Okay, because that's the fulcrum of the exploit.
Right. Its presence in unauthenticated external requests is a pretty definitive indicator of compromise, or at the very least, a highly targeted probe.
Okay, so upgrade the instance, aggressively hunt the logs for @GL introduced. That is a scenario where you, the defender, have total control over the environment, but you have zero luxury of time.
Right. But while GitLab requires you to drop everything and scour your web logs, our next vulnerability is arguably more severe, but it requires a completely different and honestly kind of jarring defender mindset.
Yeah, let's flip that dynamic. So we're moving from self-hosted to the cloud, specifically Microsoft Entra ID, formerly Azure Active Directory.
Right, the core identity fabric.
And we have CVE 2026-69836, discovered by Robert Fitzpatrick. This one carries the absolute maximum CVSS score, a perfect 10.8.
Yeah, allowing for remote code execution over a network.
Right. And here's where it gets really interesting. Microsoft noted that this flaw was exploited in the wild, but absolutely no customer action is required.
It's completely mitigated server side.
It's just a total paradox, right? Like, as a defender, a 10.0 exploited in the wild with no action required. It's like a 10.0 earthquake hits your building, but you didn't feel a thing because your landlord secretly installed shock absorbers overnight.
That's a great way to put it.
But I have to ask, is this a massive relief or a terrifying reminder of how much control we've surrendered to cloud providers?
Well, if we connect this to the bigger picture, it's really the dual reality of modern defenders. The mechanism behind this flaw kind of explains why Microsoft handled it so seamlessly.
Right, the deserialization issue.
Yeah, deserialization of untrusted data. When an application communicates over a network, it translates complex in-memory objects into a stream of bytes like JSON or XML. That's serialization.
And deserialization is just putting it back together.
Exactly, reconstructing it back into an object in memory on the server side. But the danger is that object-oriented languages use these magic methods.
Magic method.
Basically, constructors that automatically execute certain logic the moment an object is instantiated. So if an attacker injects malicious code into that serialized data stream,
The server just blindly executes it when it tries to rebuild the object.
exactly, entirely bypassing the application's actual authentication logic.
Wow. But because this deserialization happens at the infrastructure layer, deep inside Microsoft's architecture,
They can apply global mitigation upstream. They can implement strict input validation at their API gateways or, hot patch the specific class parser in the identity fabric to just reject those malformed objects.
before they ever reach the vulnerable function.
Right. It patches the hole for every single tenant simultaneously. Nobody has to restart a server.
Which is brilliant. It's the efficiency of the cloud. But you have no access to the underlying server logs.
None. You can't query a database to see if your specific tenant was targeted before Microsoft deployed the fix. You are entirely reliant on their internal telemetry.
And their willingness to notify you if your data was compromised?
Exactly. Sometimes you're in a frantic race against AI, like with GitLab, and other times you're entirely dependent on the speed of a tech giant.
So if you can't monitor the infrastructure, your defense strategy has to pivot entirely to monitoring behavior.
Right. You're looking for downstream anomalies. Impossible travel alerts, sudden privilege escalation, weird token generation. You have to assume the infrastructure might fail silently.
So your on-premise infrastructure is patched. Your cloud provider has mitigated your identity server. You're safe, right?
Wow.
Not if the actual building blocks you're downloading to write your own software are poisoned from the inside. Which brings us to the Rust supply chain attack.
Yeah, this one is incredibly insidious.
So August 20, 2026, a compromised maintainer account publishes malicious versions of 3 widely used Rust crates to crates.io.
The official registry?
Right. The crates are ArrayRef 0.3.10, Interment 0.8.7, and append-only IVEC 0.1.9.
Oh, sorry.
Over 245 million downloads combined.
They are embedded in just countless enterprise software projects. But what's really wild here isn't just the reach, it's the evasion.
Because they didn't touch the core logic of the libraries.
Right. If they modified the cryptographic functions, that might trigger an alarm during a code review. Instead, they added a type-squatted dependency, proc macro 1.
Mimicking the ubiquitous proc macro 2.
Exactly. Proc macro 2 is standard for writing procedural macros in Rust. If a developer or a scanner sees proc macro 1 slip in, it just registers as a legacy version or a standard utility.
That it blends right into the background noise.
Yeah.
This is a literal Trojan horse, but even worse, because you didn't even have to call the malicious code from the crate. Just resolving it and building the project was enough to execute the payload.
Yeah.
It's like bringing a Trojan horse into the city, and it opens itself just because you looked at it.
That is exactly what it is. And the reason this works is because the malicious code sat inside a file called build.rs within that injected dependency.
A build script.
Right. In Rust, build.rs runs during the compilation phase, before the actual application code is compiled. And it executes automatically with the privileges of the user running the cargo build command.
Wow. Because developers implicitly trust the compiler. They think it's just translating text into a binary, not, running arbitrary third-party logic on their laptop.
Exactly. It turns the build process itself into the attack vector. And they were smart about it, too. The script didn't just reach out to a known bad IP because endpoint detection would flag that instantly.
So how did it evade static analysis?
Base 64 fragmentation. The script didn't have the commands in clear text. It stored fragmented, encoded chunks of data. And during the build process, as the script ran in memory, it concatenated those fragments, decoded them on the fly.
And reassembled the payload and the command and control address at build time.
Yep. Dynamically constructed the weapon in memory, downloaded the secondary payload, and executed it, all before the developer software even finished compiling.
That is incredibly sneaky. Now, the Rust project security team was crazy fast here. They removed all 3 malicious crates from the registry within 86 to 107 minutes of publication.
Which is phenomenal incident response for an open source project, less than 2 hours.
But again, tying it back to time, in an automated CI/CD pipeline, 86 minutes is an eternity.
Oh, absolutely. A nightly build server could easily download that compromised crate, execute the script, and infect your pipeline infrastructure before human maintainers even wake up.
So what does this all mean for the listener right now? What are the defender actions?
Okay, you need to mandate that engineering teams explicitly search their local package caches, specifically the directory at .cargo registry cache. Look for any traces of those deleted crate files.
Because Rust uses aggressive local caching.
Exactly. It might be sitting dormant on a developer's laptop right now. You also need to audit your cargo.toml files and ensure you pin ArrayRef at version 0.3.9 or earlier.
Don't let it dynamically resolve to the compromised 0.3.10 version.
Right. Hardcode that limitation until you've verified your environment is clean.
Okay, let's briefly summarize the briefing for the listener's morning checklist.
Right.
First, the GitLab AI speedrun. Check your weblogs for @gel-introduced and upgrade immediately.
Yes.
Second, Entra ID. Breathe a sigh of relief, but validate your downstream behavioral monitoring. And third, the Rust supply chain. Scrub your .cargo registry cache and pin ArrayRef to 0.3.9.
That's the immediate tactical response, yeah. But, this raises an important question.
What's that?
Well, if attackers are now using AI to shrink the exploit window to mere minutes, and open source maintainers are expected to detect and remove these really complex supply chain poisons in under 90 minutes, how long until human defenders simply can't keep up?
That's a scary thought.
Right. Are we rapidly approaching a threshold where cybersecurity must become fully autonomous, just machine versus machine, simply to survive the sheer speed of the threat landscape?
Definitely something to mull over today as we watch these response timelines continue to collapse. Well, thank you for joining us on this deep dive on Cyber Mornings Daily. You are now armed with the exact knowledge you need to tackle the day. Stay vigilant, verify your dependencies, and we'll catch you on the next deep dive.